Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're solving a problem regarding dynamics, introductory problem for when we have to exchange between acceleration, position, velocity, and all those good things. This honestly is a simple problem, yet it requires some calculus. So if you're not the sharpest at calculus, you may struggle a little bit, but the concept of it is straightforward. And it's always useful to do some of these problems to make sure you're training and you're getting more comfortable with calculus, integrations, and derivations. Okay, so problem statement reads, the acceleration of a particle is defined by the relation acceleration equals 3 times the e to the minus 0.2 t, where a and t are expressed in meters per second squared and seconds respectively. Knowing that x is 0 and v is 0 at t0, determine the velocity and position of the particle when t equals 0.5 seconds. So we're given the relationship for the acceleration of a particle. We don't know anything about this other than this is how the acceleration changes in respect to time, right? So in other words, what they're giving us is a function of how the acceleration changes in respect to time. Okay, and the way it changes is 3 times e to the minus 0.2 times t. Okay, t is given in seconds, a is given in meters per second squared. That's important because else we're going to have a problem with the units, right? Because we have it to the e, so that information is actually quite relevant. What else? We're given boundary conditions. Some people learn this as boundary conditions. And these are useful because these are required when we're going to integrate because of the constant that shows up in undefined integrals. And what this is saying is when time equals 0, so that is before the particle even starts to move, the velocity equals 0 and the position equals 0. Okay, or v naught or v x naught, if that's the way that you use this kind of thing. So what are we to do here? Well, we want to find out what is the position and the velocity when time equals 0.5. If the question was what is acceleration at 0.5, it would be super simple, right? We just substitute here 0.5 times 0.2, and then we can get out what's the acceleration. But because we want the velocity, that means we're going to have to work with this equation here so that we can find out what's the velocity. And to do that, what we do is we note that the velocity, actually the acceleration, is just nothing but the rate at which the velocity changes with time. And if that is true, then it means that the velocity is just acceleration dt, and I can happily integrate on both ends so that I can get what is the actual velocity, right? So what I can do here is, if this is true, I can get this guy here and substitute where I have the acceleration, right? So this equation here becomes dv equals that dt, right? And if this is true, what I can do here is I can integrate both sides of the equation so that I can get an equation for, or a relation for v in respect to time. Okay, and this is where, calculus starts to kick in, because over here, obviously, this is going to give me the velocity, and this is a undefined integral, so I need to keep the constant that's going to show up on both of these guys here. I'm going to go ahead and do that now. Just put the constant there so that I don't forget. And there's another way to do it, if you prefer, is to say that this is going from v naught to v, and this is going from t0 to t, right? And v naught is 0, so therefore you end up with this. Both are going to, there's slightly different ways of doing it, but they're going to give you the same answer. Okay, so if we want to do this integral, we can get the 3 out of the way because 3 is a constant, and we're left with the integral of minus 0.2 t dt. Okay, and this is an integral that we can do by substitution. I'm going to note that 0.2 is the same thing as 20 divided by 10, which therefore is the same thing as 2. Wait, whoops, that's not true. 20 divided by, no, 2 divided by 10. That makes more sense. Okay, 2 divided by 10, which is the same thing as 1 over 5. So I'm going to go ahead and say this is 1 over 5 here. And if it's 1 over 5, it's the same thing as t over 5, right? And I think this is an easier way to deal with this. And I'm going to go ahead and substitute where I have this. I'm going to substitute that by u, which is a letter generally folks use for this kind of substitution. But you can choose whatever letter rocks your boat. Okay, I'm going to say that's u. And then what I need to do is I need to derive u. If this is true, then I'm going to need to derive u. I'm going to do it the other way around. Put it over here. U is this. Okay, and then what I need to do is derive u in respect to time so that doesn't make sense. That doesn't make sense. What I need to do is substitute t minus 5, t over 5, and call that u. That makes sense. Because then I can substitute and make it simple. Okay, so this will be minus 1/5, which means that dt is equal to minus 5 times du. All right, so what I want to do now here is substitute. I want to find this integral here. And to find this integral here, I'm going to go ahead and substitute. This is equal to the integral of e to the u. That's the substitution I want to do. And if I want to substitute dt, dt is minus 5 du, so times minus 5 du. Okay, now this is way simpler. So this is minus 5 integral of e to the u du. And this integral is super easy. Oops, this integral is super easy. So this integral is just e to the u. Okay, so now I can go back and say if this is true, I can substitute it back. If it's minus 5 to the u, and u is this, then this means that this is the same as minus 5 e to the minus t over 5. And this is what I want to know. Okay, so minus 5 to the e to the minus t. Okay, so this means that this will be equal to the constant plus 3 times minus 5 e to the minus t divided by 5. Brilliant. So therefore, velocity equals a constant plus a negative 15 e to the minus t divided by 5. Okay, and this is how the velocity changes with time. So another way to denote this is how velocity changes with time. Velocity in respect to time is a constant minus 15t. So right now, if we want to find out what's the velocity when time equals 0.5, I can substitute it here. And we would get a number out of this. However, we have this constant that we haven't addressed yet. That's where the boundary conditions show up. Okay, and the boundary condition says that when time equals 0, and my velocity equals 0 too, right? It's v naught. So if that's the case, then this means that, okay, if v0 will be equal to constant minus 15 e to the 0, right? Because time is also 0. If this is the case, then it means that constant will be equal 0 equals constant minus 15, and therefore the constant I'm looking for is just 15. Okay, so now I can go back to this equation, this velocity equation, or velocity relationship. That's how velocity changes with time, and I can say confidently that this is 15. Okay, so this is how velocity changes with time. It's 15 minus 15 to the e to the minus t over 5. And note that if time is 0, right, if time is 0, then this whole thing here goes to 15, and then it's 15 minus 15, which is 0, which satisfies our equation. All right, so now what I can do is